for years been, we haven't even copyrighted our material. We allow people to copy it, to give it away. That's what we want.
Material, not copyrighted. Use any way you want.
My name is Eric Hovind.
My name is Eric Hovind? Aw, hell no.
Welcome to Paulogia, where a former Christian takes a look at the claims of Christians. I took a bit of a break from creation today after doing the in-depth series on Eric's Genesis Paradise Lost movie, but I've also been anxious to cover Eric's other opus achievement, his completely original creation seminar, Beginnings.
There are actually 6 different kinds of evolution.
Six types of evolution, that's it!
Logicked.
What do you think you're doing, man?
Am I in hell? I thought there'd be more country music.
Well, I couldn't exactly leave here and come up to where you are, could I? But I'm not sitting by and letting some little upstart YouTube channel rip me off.
Whoa, rip you off. You have your series with Kent Hovind, and I respect that. My series is entirely about his son, Eric.
Yeah, nice try, asshole. I'm not buying your fancy de-aging special effects voodoo. It's a smug Hoven on stage trying to redefine evolution as 6 things to an audience of dimwits. I know a Kent when I see him, and I covered this already in 2014.
If you're going to get into a debate on evolution with anybody, you better first define what you're talking about.
Can we talk about musical evolution? Because I'd much rather talk about the transition from blues and rock and roll to heavy metal than whatever you're going to talk about.
Listen, Logicked, I didn't know. I mean, back in 2014, I still believed in a young Earth. It makes sense that Eric would have been a little inspired by his dad, but I'm sure any similarities are entirely superficial.
First of all, we've got cosmic evolution.
That is the origin of time, space, and matter, the Big Bang. Chemical evolution, stellar and planetary evolution, organic evolution, macroevolution, microevolution.
So, I'm not the one ripping you off. Eric has been ripping off his dad.
Well, okay. The shady dealings of the Hoven family are kinda legendary, even down here in hell. Did you know they have a whole compound reserved in the Conman Snake Oil District? But either way, man, you should know better. Just stick to the topics I haven't already covered with Kent, and everyone will win here.
Okay, fresh topics. Let me just scan ahead here.
All the matter in the universe was concentrated into one very dense, very hot region that may have been much smaller than a period on this page.
Already did it.
If
the merry-go-round is spinning clockwise, when the kid flies off,
Nope, did that one too.
Jupiter is
they're cooling off. They're radiating more heat than they gain from the
Oh,
sun.
hey, Jupiter. I don't think I've covered Kent talking about Jupiter cooling off, so there. You can start with that one.
Jupiter. Perfect. Thanks, Logicked. Just send me back to Earth and I'll get on it.
About that. Teeny tiny problem. I don't actually know how to send anyone back. I just know how to summon people here, apparently. So, this is awkward.
Want to help debunk the Hovens?
Yeah, whatever.
Some of the planets are still hot, but they're cooling off.
Jupiter is cooling off.
They're radiating more heat than they gain from the sun.
It loses heat twice as fast as it gains heat from the sun. So it's losing heat very, very rapidly.
Interesting. All right. Well, I have a few questions to start with. Does Jupiter actually radiate more energy than it receives from the sun? Notice that this is not the same as asking, is Jupiter cooling? To assert that Jupiter's actually cooling is more than just an assertion that it emits more energy than it receives. It also means its temperature is declining over time. So that's the second question. Is Jupiter actually cooling? Is it getting colder? Has this been measured? And if so, Eric, what does very, very rapidly actually mean? That's an incredibly subjective way of putting it, so what's the actual rate of cooling we're talking about here? How much energy every second, for example? You do sort of specify, you say it's twice as fast as it gains heat from the sun. So first, is that true? And secondly, what is that rate? And if it is true, then specifically what's causing the difference in these rates? Is Jupiter really just cooling down so fast, or is there something else going on? Since this one assertion you both make is going to be the foundation of your entire argument, it sure would be nice to get some of these details so we know precisely what the assertion even is. But we're not going to get any, and I'm used to that with you, so forget it. The first step as I see it is to figure out where this claim comes from, or at least could come from. You don't say, but I found a very similar claim to yours on creationscience.com. And in the citations is a book called The Structure of Planets by someone called G.H.A. Cole from 1978. Newer than I expected. And according to the citation at least, it has the quote, "Jupiter radiates into space rather more than twice the energy it receives from space." Now, I haven't seen this book. Those who've watched my other creationism debunks will know that normally I'd track down a book if I found it important, but I didn't get a chance to this time around. You'll have to forgive me this once. The only real reason to track it down would be to see if it says what this random creationist website says it says. Kent and Eric didn't even cite it, and what it says isn't exactly unbelievable, and I can find a similar number elsewhere, in sources the book probably took it from. Here's a paper from 1981, Aged Like a Fine Wine, that has a handy table of numbers from other sources, conveniently from 1978 and previous, showing their measurements of just what we're interested in. So we have a variety of ratios here between 1.6 and 2.5. So I think it's safe to say that regardless of whether the book was exactly right about the ratio being rather more than 2, it's probably somewhere around 2. And if that is actually just the planet cooling down, then yeah, considering the amount of energy Jupiter gets from the sun, that could be called a very rapid decline. Not as rapid as you might think, though. Jupiter's at about 5.2 astronomical units from the sun, or 5.2 times as far away as the Earth. So by the inverse square law, Jupiter gets about 1 over 5.2 squared times the solar energy per square meter that the Earth does, or about 1/27th of the amount of solar energy. So if the sun is 27 times less intense at that distance, then if Jupiter radiates away twice that much energy, it's about 13.5 times less per square meter than what the Earth receives from the sun. So to say Jupiter radiates away twice as much energy as it receives from the sun is a much less significant statement than if you made a similar statement about the Earth. The amount of energy emitted is still a big number, but it's also a big planet, with big internal temperatures. But the problem I bet a lot of viewers have already noticed here is that big old giant if in the premise of your whole argument. Actually, a couple ifs. Firstly, your argument only applies if Jupiter is really just an inert ball of gas radiating away heat that it initially had from accretion or wherever else while generating nothing of its own, just declining in temperature over time. And second, your argument only applies if that rate of decline is actually fast enough that Jupiter could no longer be radiating away any thermal energy accumulated during its accretion anymore. So is it as simple as you're presenting it to be, or is there more to this than you're letting on, Mr. Hoven?
But Jupiter is still very hot.
It's just not logical to say Jupiter, which is losing heat, is billions of years old.
It couldn't.
Right. Well, I guess that's the answer I should have expected. Meaning no real answer, just nothing can lose heat for a long time and still not be totally cold, because I say so. Come on, dudes. So let's dig into this a bit, as if there's even anything significant enough in this tripe to dig into. I hope most people noticed that Kent and Eric's statement here is oddly general, that something just cannot radiate heat for billions of years without running out of energy, full stop. But of course it can, because the possibility of that is not based on some binary yes or no answer to the question, does this time period seem long to Kent and Eric Hovind? It's also based on how much energy the planet had to start with, and the rate at which it's radiated heat throughout its history, and whether it's generated any extra heat during that time. Not a single one of which Kent or Eric bothered to even mention. It's like insisting that you can't drive from Calgary to Vancouver on one tank of gas, without bothering to consider the size of the tank, or fuel efficiency, or whether it's a hybrid and was charged up along the way. It's an assertion you can only make by ignoring most of the relevant information that you two have presented as if it's an argument. It's not, and because it's not, there's really no reason I shouldn't just stop right now. But I won't. I'll take it more seriously than it actually deserves and consider it just a bit more deeply. So the first question I'd like to answer is whether it's even within the realm of plausibility that a Jupiter with no internal heat generation could be radiating as much heat today as it is solely from the thermal energy stored during its accretion. Now the full math on that is an awful long way above my pay grade. A planet is a lot more complicated than some idealized ball of one or two elements with a constant rate of heat emission. And that's about the most I can manage. Different elements in different states radiate heat at different rates, and the overall rate would probably slow down as the planet cools. And this just isn't something I know how to calculate. But for my purposes, that's acceptable, because after all your so-called argument actually is nothing can lose energy for billions of years and still have any energy left to lose. Incredibly vague, incredibly general, and there's no indication that you've based it on anything except your own intuition. You just feel that this is obviously ridiculously improbable and therefore can be discounted as a possibility. So a very rough rough check on whether it actually is obviously ridiculously improbable or not will be plenty good enough. So we're going to assume for now that there is no internal heat generation in Jupiter, at least not since its accretion. That's almost certainly not true, and we'll get back to that, but for now we'll call it true. So how much would this temperature decline over time based on the energy loss we're actually talking about? I shouldn't have to ask because these figures are critical to the success of your argument, but well, I've already covered that. Now, first I wanted to see if there was some study that'd show the calculations and just hand me the answer. So I looked around and I found a couple of papers as well as a whole bunch of books written for more of a popular audience that just kind of assert that the heat emission of Jupiter could well be from residual primordial heat from its accretion. And okay, fine, but since I didn't really find any concrete calculations that really convinced me, I'm not going to rely on any of that. It's probably out there somewhere, I'm sure somebody's done this, but I didn't find it, so never mind, I don't need it anyway. The same paper we looked at before with the list of energy balance estimates also includes the estimates for absorbed solar energy and emitted energy, the energy balance being the ratio between these. So the absorbed solar energy is 5.014 times 10 to the 17 watts, and the emitted energy is 8.365 times 10 to the 17 watts. So the difference is 3.351 times 10 to the 17 watts. Another way to say watts is joules per second, so that means each second Jupiter's emitting about 335 quadrillion joules more than it gains from the sun. Wow, that's a big number. But I'm not just going to say that number looks big, therefore it's impossible. I just want to know if it's anywhere near possible, to know if it's even worth considering. Because your argument is basically, it's not worth considering because it's nowhere near possible. So let's use this specific heat calculator. With this, we should be able to figure out how much the temperature of a specific mass of a specific substance will decrease when a specific amount of energy is taken out. This certainly leaves out a lot of real-world variables that would have to be taken into account when you're talking about a real planet, but we just want a really rough approximation here, so we're going to treat Jupiter as an idealized ball of hydrogen and helium, which is an oversimplification, and this calculation also won't account for the likely increased rate of energy loss further back in time. But if the whole idea is as obviously ridiculous and impossible as you imply it is, to the point that any cooling object, regardless of starting temperature or the rate of energy loss, would have to be cold after billions of years, then it shouldn't matter, right? When we extend the results to a multi-billion year timescale, then by your reasoning we should still get back a ludicrously high decline in temperature that makes us shake our heads and go, no way, that just can't be right. Jupiter has to either be generating heat or be younger than we thought. But enough jabbering from me, let's plug in some numbers. So we have the energy, that's 335 quadrillion 100 trillion joules. And we'll stick a negative on there because we're taking that much away, not putting it in. What we want to know is the change in temperature, so we're going to leave that blank. The mass we'll put in terms of Earth masses, which Jupiter is about 318 Earth masses. And we're not going to use the substance selection, but I'll show you what it gives us anyway. So if I choose hydrogen, we get a specific heat of 14,300, and if I choose helium, we get 5,193. Now, Jupiter's roughly 90% hydrogen and 10% helium. There's a few other negligible elements in there too, but that's mostly what it is. So if we average that out with a 9:1 ratio of hydrogen to helium, we get 13,389. So that's the specific heat we're going to use. And the result is we get a change of temperature of minus 0.000000000000013 Kelvin per second. I think I read all the zeros. That's a really small number. And suddenly your intuitive assumption that this is totally impossible seems slightly less obvious. But over billions of years, even small changes can add up to really big ones, right? You and I know all about that from the evolution discussion. So what is it over 4.5 billion years? Well, over 1 year, the change is 0.000000041 Kelvin. Multiply that by 4.5 billion, and the total decline in temperature is 1,845 Kelvin. Huh. Odd. The way you were talking as if it's totally unreasonable to think it's even possible. I thought that number would have to be up in the millions or billions. But even so, I can't deny it is still a big decline. So what range of temperatures are we actually talking about when we talk about Jupiter? Well, the surface is about minus 145 degrees or 128 Kelvin. That's pretty cold. The core temperature, on the other hand, is thought to be around 24,000 degrees. Let's say the average temperature is right in the middle, 12,000 degrees. So does that mean that if Jupiter generated no heat at all, it would have only declined from 14,000 degrees to 12,000 degrees over 4.5 billion years? Well, no, probably not. It'd likely be some amount worse than that once everything, especially the change in cooling rate over time, is taken into account. But it certainly puts to rest your simplistic argument that, ha! That number's big! Therefore it's obviously impossible, can't happen.
Some of the planets are still hot, but they're cooling off.
Jupiter is cooling off.
They're radiating more heat than they gain from the sun.
But Jupiter is still very hot.
It's just not logical to say Jupiter, which is losing heat, is billions of years old.
It couldn't.
But now let's get back to the reality you chose to avoid in the framing of your argument. The fact is, Jupiter is not just some inert ball losing heat while generating none. I pointed this out before. There's a major difference between the claim that Jupiter radiates more energy than it receives, and the claim that Jupiter is actually getting colder as a result. To consider these to be equivalent, you'd have to assume that there can be no mechanism by which Jupiter could possibly generate heat. But there can, and we know for a fact that objects in our solar system generate heat. The most obvious example being the sun, which generates way more heat than anything else around. But that's not a very useful example, because that's a fusion process that obviously doesn't happen in Jupiter. But it's a baby step towards where I want to go, because it demonstrates the basic idea that there can be reasons an object radiates heat that go well beyond, it was hotter before and it's getting cooler now. This stuff is a bit more complicated than just that any given object that emits heat, like stacked up 3 little heats in a neat little pile 3 days ago and then emitted heats at a steady 1 heat per day until now it has no more heats in the heat stack. Anyway, there are much better examples of solar system objects that generate heat, such as planets. In the case of Earth, this generation tends to happen largely because of radioactive decay. But this doesn't really apply to gas giants like Jupiter. But there are a number of other processes that can pick up the slack. I'll tell you about a couple of them. One of them is the Kelvin-Helmholtz mechanism. Basically, the surface cools, causing it to contract, and the contraction provides the energy that heats the core, and the core radiates out the heat. So in this process, some cooling does occur, at least on the surface, but ironically, the cooling is what actually causes Jupiter to warm itself. And this process would mean that Jupiter shrinks gradually over time. The number that's commonly given is that its diameter would shrink by about 2 centimeters a year. And Kent and Eric, before you go off proclaiming that, aha, a planet can't shrink at 2 centimeters a year for billions of years and still, I don't know, not have shrunk to nothing and winked out of existence or something, keep in mind that 2 centimeters per year over the 4.5 billion years of Jupiter's existence is only 90,000 kilometers. Not even as much as its current diameter of 143,000 kilometers. Another possibility is the differentiation of hydrogen and helium. Liquid helium is propelled gravitationally towards the center of the planet, raining, so to speak, through the metallic hydrogen, causing friction which generates heat. This is thought to be a big contributor on Saturn, but it applies on Jupiter too. So the point of all of this is Kent and Eric, no matter which angle we choose to approach this from, there's a viable explanation for the energy balance regardless. But there's an even more important point here, which is if none of these ideas had ever been considered, if none of the calculations had been done, if humans had no explanation, no idea how this happened, would that mean there is no explanation? Well, no, of course not. Us lacking an explanation for a phenomenon does not mean that phenomenon can't be explained, it just means we haven't explained it yet. If all the other data we have about the solar system and the universe point to Jupiter being 4.5 billion years old, but we happen to have a couple outstanding questions like, but why isn't it colder though? We wouldn't just throw up our hands and assume it must be 6,000 years old then, Bible, 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 like you have. That's not a way to learn about the world, it's a way to avoid learning about the world. But that's all hypothetical because although we do have more to learn about Jupiter, there are several viable explanations for its heat radiation, so you're talking about a problem that doesn't exist and hasn't for like 40 years. All that's really left to argue about is which of the processes are responsible for it in which proportion, and if there's any other ones that haven't been thought of yet.
But if Jupiter was created just a few thousand years ago, like the Bible teaches, now that's an explanation.
Sure, or you can just say Bible and move on, whatever.
Jupiter has a little moon called Ganymede.
I assume that little is meant to be a bit of a joke. I mean, Ganymede is Jupiter's largest moon and the largest moon in our solar system. Indeed, it's even bigger than the planet Mercury. Kent knows this and is making a joke, right?
Ganymede has a strong magnetic field. When it was discovered about this strong magnetic field, they said, wow, that's strange.
It was back in 1996 when Starship Galileo gave scientists their first reading of the Jupiter system. It was a very exciting time to have some predictions about the system to be vindicated with data, and other ideas shown to be false. Ganymede's magnetic field was one such surprise.
That indicates a hot core, and yet Ganymede should have cooled off billions of years ago.
But it didn't.
The reporter quoted on Kent and Eric's slides is paraphrasing the December 1996 write-up in Nature, which noted that bodies as small as Ganymede are unlikely to have sustained the necessary fluid motions for billions of years because the heat can escape by thermal conduction. So the puzzle remains. However, just because something starts as a puzzle doesn't mean that it is unsolved. Later in the issue, the research team attributes the sustained existence of Ganymede's magnetic field to an effect called tidal heating. When two celestial bodies interplay, like a planet and orbiting moon, The effects of gravity on each other get stronger during the parts of the orbit that are closer together, and weaker when they are further apart. And the portions of the bodies facing each other also feel more gravitational tug than the far sides. As such, these planets and moons end up getting squished and squashed from rounder shape to oval shape due to the gravity pull. On Earth, this is most noticeable by the surface water swelling up into tides, thus the name tidal heating, even for bodies without water. But the same squishing and squashing is happening to Ganymede as it orbits Jupiter. This causes significant friction, which in turn causes heat, enough to have allowed sustained convection of a liquid core over billions of years. When this was first proposed, the hypothesis was untested, and the Hovens jumped on the idea of an unsolved mystery, deliberately ignoring the solution proposed in the very same paper. And of course, this matter has been studied in the decades since, with papers in 1997, 2001, and 2007 affirming tidal heating as a sufficient cause, and continuing to refine the dynamical thermal models of Ganymede and other moons,
I wonder why it still has such a strong magnetic field.
indicating that models must somehow account for cooling, and they do. The Hovens continue to bring up this side issue about Ganymede,
Ganymede has a very strong magnetic field. Well, not very strong, but a strong magnetic field.
but ignore the other surprise from those initial probes, that its highly impacted and disrupted surface has every indication that the moon is extremely old.
The Sahara Desert is growing. Well, how long has it been growing?
Since it randomly popped into existence in 1972?
The Sahara Desert has what's called a prevailing wind pattern. The wind almost always blows the same way.
Yeah, like everywhere else. This isn't unique to the Sahara. Now, I'm not necessarily saying you were suggesting that, but just in case you were, I wanted to mention it.
This creates a problem. The hot air blows off the desert and kills the trees next door, and that area becomes desert. The process is called desertification.
Well, the northeasterly prevailing winds do help to keep the desert dry a little bit, but you're presenting those like the reason why the desert is currently growing, because hot air is killing trees to the south for some unstated reason. And I would say that's oversimplifying it just about to the point of flat-out dishonesty. The climate's a complex thing, and it's rare that you can adequately express the causes of features like this in a one-sentence soundbite like you tried to.
They've done quite a bit of study on Sahara that's pretty obvious it is growing.
About 4 miles a year.
All right, so before we go back to why the Sahara is growing, let's look into whether it's growing at all, and if so, how fast. So considering that the desert stretches all the way to the north, west, and east of the continent already, then what it means for the desert to be growing is the areas to the south are seeing a gradual reduction in the amount of precipitation they're getting, and eventually falling below the threshold where they would be called a desert, which is about 100 millimeters a year. And indeed, it is true, the transition area between the Sahara and sub-Saharan Africa, called the Sahel, has been seeing this reduction in rainfall, at least since 1900, and as a result, the Sahara has grown at least 10% during the 20th century. That is an absolutely massive increase, although it's an awful lot less than 4 miles a year. The Sahara is about 1,100 miles from north to south, so 10% of that is something like 100 miles, but 4 miles per year over a century is 400 miles. Maybe you're trying to suggest that it's sped up over that time due to climate change or something like that, but you don't say that, and I haven't found any sign of that number anywhere. So are you sure that's the rate you want to go for, Eric? Because it seems a little overkill. But it's alright, if you're a little off with the rate, it doesn't matter. The fact remains that the Sahara has been expanding south at an alarming rate for a while now. And unfortunately, that extreme speed of desertification seems to have a lot to do with human activity, both in terms of land use by the local people and overall climate change. But now as for the reason why the Sahara is a desert at all, well, the main factor has nothing to do with us. Human land use may have had something to do with accelerating the process at some point in history, but it would have happened anyway. See, there are recurring patterns in the movement of the Earth, and the seasons aren't the only climate cycle occurring because of the Earth's tilt. There's another cycle of about 41,000 years long where the angle of the Earth's tilt goes up and down by about 2 degrees. And the result of this wobble is that at different times, different areas receive more direct sunlight, changing their climate and the overall climate of the planet. Over the past few thousand years, this angle has changed such that the Sahara region is cooler. Yes, I said cooler, not hotter, and this is a big problem because when the Sahara is warmer, the air pressure is lower, allowing an inflow of air from the Atlantic Ocean, which increases humidity. And naturally, this results in rain, which resulted in the Sahara being a big green happy grassland thanks to the summer monsoons. You can see a little hint of a similar phenomenon today when, in the summer, the rainfall in the southern Sahara improves dramatically. But as the Earth's tilt changed over a few few thousand years and the temperature dropped, those monsoons that helped the Sahara stay green became less and less common, to the point that now North Africa is, well, not quite so green and happy. But the area south of it is great, so that's a consolation prize, I guess. So the fact that the fundamental cause of the desert is local and recurring means a couple of things. Firstly, the desert is not going to grow forever. The entire African continent is not going to turn into a sandy wasteland. And secondly, the desert that's there right now is not going to be there forever. It'll take about 15,000 years or so, but eventually it'll most likely return to the healthy green zone it's been many times over in the past. A bit late to help the displaced residents, but hey, better than nothing, right?
You go backwards in time from what it is today to what it used to be.
The Sahara Desert is probably about 4,000 years old.
Why did you both include the possible future extent in your slide about the present size of the Sahara? You both show it being 1,300 miles from the north tip of the present extent to the south of the possible future extent. Come on, guys, pay attention. You've only been using these slides for what, like 20 years? But I do appreciate that you cited a paper, so here it is. Now, this explains the results of a climate simulation that was done to determine changes to the climate thousands of years ago, which I'm surprised you take as established fact just because of this one paper when you can't, at least, I don't know about Eric, typically don't even accept direct, non-simulated evidence about past events like Noah's flood or the lack thereof, and you don't even accept the much more easily verified results of climate simulations from the same scientists who wrote this paper based on direct observations of modern phenomena, by which I mean you deny climate change.
I don't think we could cause global warming. It's stupid. I think it's another excuse for government intervention into your affairs and my affairs.
So many people get so worried about, well, what are we going to do with climate change and what are we going to do about this? God is the one who controls it. We don't.
So you think someone should be criminally investigated and maybe jailed if they think there's no climate change? I don't think there's climate change.
Kent, the scientists who wrote that paper you're relying on are all climate scientists. The principles and some of the tools they're relying on here are the same ones used in research about the modern climate. You deny that and you accept this. I don't get it. And what's more, plenty of these people have done work on climate events a whole lot older than 4,000 or 6,000 years. One example of which being the paper you cited. The simulation they did covered a 9,000 year span. If, as you seem to think, the results are an absolutely accurate depiction of the events of 4,000 years ago, it's just as accurate a depiction of events from 9,000 years ago. And much more importantly, the paper doesn't even say that the desertification of the Sahara started 4,000 years ago, which, spoiler alert, you're going to say corresponds to the time after Noah's flood, which proves that the Sahara originated after that event. But the paper doesn't say it started 4,000 years ago, it says it started 5,400 years ago. 1,000 years too early for you. And on a 6,000 year timescale, that means something. So your source directly contradicts your narrative. What's your excuse?
I have no reason to doubt that, but I do have a question.
You have no reason to doubt most of the stuff you doubt, but you do it anyway. I can only imagine the denial if this paper rejected the global flood. Actually, it does. But you didn't read it, so you assumed it supported you somehow. Whoopsie.
If the Sahara is only 4,000 years old, why don't we have a bigger desert someplace?
We do. 2 of them. At the poles. Sure, they happen to be colder, but they're still deserts, because desert is defined by precipitation.
Why would the biggest desert on Earth be less than 4,000 years old?
Kent, according to the paper you chose, it's not. It could not be more clear. In an ensemble of 10 simulations, the abrupt desertification in North Africa begins at 5,440 plus or minus 30 years before present. Here's a picture if that's too complicated for you. Either you didn't read it or you're lying. Take your pick. So if you accept your paper's conclusions as fact, as you seem to, then you must accept you're wrong. And if you deny these conclusions, then your argument loses its foundation. You're kind of damned if you do and damned if you don't here. But I agree the Sahara's growth speed is unusual among deserts, and the reason it's unusual is simple. The cause of the Sahara Desert is the response of a very specific geographic region to a specific periodic event, and other deserts are geographically different regions from the Sahara, and have different causes from the Sahara. Different stuff happens in different places that have different features, Kent. What exactly is your reasoning here? That if one hot desert is large but young, therefore there must be another hot desert that's even larger because why? What process necessitates this? Does older by definition mean bigger? I mean, clearly not. Deserts don't expand infinitely, not even the Sahara. Their location and growth are limited by geography and climate. If those factors enable higher than desert level precipitation in most areas, but not in the Sahara region, then things are going to play out just like they have. And those factors do that. So they played out like they have. Kent, didn't your teacher ever tell you there is in fact such a thing as a dumb question? Here's a better question. Based on what you've said so far, you seem like you respect the work that's done on determining the ages of deserts. So I'm curious what your opinion is on the research that shows that other deserts, like the Namib, the Atacama, the Australian deserts, for example, there's more, are at least several million years old. Do you accept that research, along with the fact that the Earth is more than 6,000 years old? Or do you need someone to run a simulation for you first? You seem to find those convincing.
Because the creation worldview says
6,000 years ago, God created everything. 4,400 years ago, there was a flood.
Despite the fact that your own source says it doesn't fit that worldview at all, it does come an awful lot closer than most other deserts. Suspiciously close, I might even say. Almost like you cherry-picked this one in particular and ignored all the rest for some reason. Huh. Nah, couldn't be.
It's pretty hard to have a desert under a flood. So the desert couldn't start growing until the floodwater went down.
One anomalous year doesn't really make a desert stop being a desert, but you seem to think it's a problem, so it's lucky that if you accept what your chosen paper says, there was no flood for the desert to be under, and that desert's been growing there since 1,000 years before that flood was supposed to have happened. Problem solved, yeah? Or problem created, however you want to look at it.
So I predict, based on the Bible, the biggest desert in the world will be less than 4,400 years old. It is. Wow.
Excellent. So you made the prediction, and based on the evidence you presented yourself, your prediction failed, and the Bible's false. I'm glad we could agree.
The Earth is like a big magnet.
Now, the magnetic field around Earth is getting weaker because magnets over time lose their magnetism.
This is basically correct. Magnetic fields weaken. There's lots of reasons, but close enough for this discussion.
The Earth's magnet has lost 10% of its strength in the last 150 years.
It's declined by about 10%.
10 to 15% reduction over the past 150 years is consistent with the literature. Carry on.
Wow. Almost 40% in the last 1,000 years. It's getting a whole lot weaker than it used to be.
I couldn't find where Eric got this number from, but the Answers in Genesis book on the Bill Nye debate repeats this number, with the footnote not providing a source, but just the idea that magnetic fields reduce 5% per century. I have a feeling that treating this as a linear progression is going to be a problem.
If the magnetic field is getting weaker, that means that it used to be stronger. Exactly right.
Very good, Eric.
Well, that's normal for magnets to lose their strength, but that's interesting. That proves the Earth is not more than 25,000 years old. This is a limiting factor.
The references on Kent's slide, both Donald Young's Astronomy in the Bible and Henry Morris's Scientific Creationism, put a 10,000-year maximum on the Earth's magnetic decay. Of course, neither provide any sources or references or formulas of any kind for this number, but even if they did, that doesn't match Kent's 25,000-year number. Answers in Genesis suggests 20,000 years, citing a 1973 Institute for Creation research book called Origin and Destiny of the Earth's Magnetic Field by Thomas Barnes. This document from nearly 50 years ago wasn't even contemporary at the time, using data only from 1883 and relying on a simple linear decay model of the Earth's core that even then failed to explain basic magnetic fields observations like the existence of the non-dipole field, the fluctuations in the dipole moment, the reversals in field polarity, or the continuous changing fields in the geologic record. The dynamo model of the Earth's core, a rotating, convecting, and electrically conducting fluid acting to maintain a magnetic field, is nearly universally accepted today because it can explain all the observed features and data. Barnes' work explains only a handful of isolated data points that are over 130 years old, and doesn't do it particularly well.
Well, how far back can you go before that starts causing a problem? You go back too far in time and you got some serious issues with Earth because of Earth's magnetic field.
It might be a problem if the evidence showed a consistently weakening magnetic field forever into the past, but that's not what the evidence shows. More on that soon.
Also, this points out that
Carbon dating can't work, because as the magnetic field declines, more radiation gets in, and that's what forms carbon-14.
Neither of the Hovens bothered to explain how the magnetic field and carbon-14 would affect each other. But the Thomas Barnes material we've already spoken of drew on the findings of this 1956 paper that a decrease of magnetic field is followed by an increase in cosmic ray flux, and thereby an increase in the production rate of carbon-14, as Kent suggests, because the magnetic field deflects the charged particles making up cosmic radiation. It might be worth taking a second to remind everyone how carbon dating works. Earth's atmosphere is constantly bombarded with cosmic rays. When these rays collide with atoms in the atmosphere, it causes reactions, which in turn causes neutrons to be ejected from a hydrogen nucleus, leaving a radioactive type of carbon known as carbon-14. While they are alive, plants, and things that eat plants, absorb both regular carbon-12 and radioactive carbon-14 in the same ratio as they exist in the environment. When an organism dies, it stops bringing in new carbon-14. So, as the carbon-14 it already has starts decaying into carbon-12, the ratio starts shifting, and a time since death can be calculated based on that. So indeed, if the magnetic field were many times stronger than it is today, there would have been less cosmic radiation entering the atmosphere, and therefore less carbon-14 would have been produced, and therefore the starting ratios of carbon-14 to carbon-12 would be different, affecting the age determined by the current ratios. But of course, scientists are aware that the C14 to C12 ratio hasn't always been exactly the same. However, determining the historical fluctuations in this ratio is possible by utilizing a study of tree rings, dendrochronology, and carbon dating individual rings to find any deviations from expected radiocarbon content for their established ages, like shown in this paper, resulting in this graph, which provides support for the reversing polarization model of Earth's magnetism that we'll get to in a minute. Nothing here shows the kind of linear increase that the Hovens are proposing. For example, Barnes extrapolates a magnetic field 19 times stronger in 4000 BC than it is today, when clearly the evidence shows it was only half as strong as it is now.
1949, when they first invented carbon dating.
Why are we going to hear a story about when they first invented carbon dating? If we wanted to discuss the reliability of modern air travel, the experiments of the Wright brothers wouldn't be relevant.
The leg of a mammoth dated 15,000 years old, but the skin from the same mammoth dated 21,000 years old.
Let me just say it's amazing that we live in an age where a determined YouTuber can find scans of a 500-page magazine published 70 years ago. But here we are. Clearly the Hovens didn't expect their audience to ever actually check on these claims. So they footnote Nature's Deep Freeze, Natural History, 1949. While this is a perfectly good article about some of the impressive mammoth finds of the 1940s, there are no references anywhere in the article about carbon dating any of the specimens found in Fairbanks Creek. Multiple specimens, by the way, including a baby. Somehow I'm doubting that either Hovind read this. Instead, these specific numbers on the Hoven slides come from U.S. Geological Survey paper 862 from 1975, which Kent will cite on the next slide. Let's see. The specimen dated 15,380 years old was fresh from the lower leg of an adult mammoth found in 1940 in frozen silt 26 meters below the surface. The specimen dated 21,300 years old was the skin of the baby mammoth, found miles away in a beaver dam 8 years later by an entirely different team. These were not from the same mammoth. To add insult, the report notes that the second specimen had been soaked in glycerin by the collector, something well known to mess with the carbon levels in the sample. This isn't a simple mistake by the Hovens. This is fraudulent misrepresentation.
They carbon dated another mammoth. The front half was
29,000 years old.
The back half was 44,000 years old. Slow birth?
Sadly, the Geological Survey referenced on Kent's slide should really have been on the previous slide. The claims and dates provided are not found in the survey, which has prompted Talk Origins and some books to dismiss these dates as entirely unfounded. But maybe not so fast, everyone. According to the Eastern Arctic Seas Encyclopedia, the Velosevich on this slide is Konstantin Adamovich Velosevich, a Russian geologist who in 1900 was exiled to East Siberia for political activities. He found himself assigned to an Academy of Sciences exploration of the Yana-Indigirka lowland in 1908, where he discovered the remains of a mammoth from the Sanga-Yuryak River. In 1997, this Russian paper on radiocarbon ages of mammoths in northern Eurasia included an appendix listing hundreds of mammoth samples that have been carbon dated throughout history. Among them is a specimen from Sanga-Yuryak, sample T170. And T170 appears in the table 4 times, indicating that it has been dated 4 times, each returning different results. 2 of the dating estimates, 44,000 years and 29,500 years, match the Hoven slide exactly. This 2003 paper from the Netherlands confirms this finding. T170 is listed 4 times with 4 different dates, 2 matching the Hoven claim. Now, there are many reasons that a dubious result stemming from a biological sample taken from a political exile geologist in 1908, stored and maintained in undocumented conditions for nearly 60 years before undergoing dating testing, might not be the kind of outlier upon which we'd want to build a case against the hundreds of results in the same paper that agree with each other. For example, we don't actually know if T170 was from one animal or multiple animals. What we can say is that while the Hovens were fraudulent in their misrepresentation on the previous slide, this slide might have technical veracity. If we forgive the unforgivable error in citing the wrong source, that is.
That's just one more element to show us that carbon dating simply does not work.
What's baffling here is why the Hovens are even bringing up carbon dating in a discussion about the age of the Earth. Because of the short half-life of carbon-14, it isn't useful in dating anything older than about 50,000 years. And even then, only things that were once alive. Neither apply to the Earth. It's other forms of radiometric dating, uranium lead, potassium argon, rubidium strontium, and others, that are actually relevant to the age of the Earth. The Earth's magnetic field has absolutely no effect on any of these planet aging methods. But the Hovens are hoping their viewers don't know that.
The textbook says, well, yes, Hoven, the magnetic field is declining, but that's because it's part of a pattern of reversals.
Some people say, well, the Earth has reversed its magnetism.
At present, the Earth's magnetic North Pole is near the geographic North Pole. But that hasn't always been true. The magnetic North and South Poles have switched places many times over the course of Earth's history. The last swap was about 780,000 years ago, before which compasses would have pointed south.
Nobody has a clue how it even could reverse. There is no proof it ever has, and there are no magnetic reversals locked in the ocean floor.
Is what they're referring to. They find areas of strong magnetism and weak magnetism.
Not magnetic reversals.
The evidence that has convinced the scientific community that the Earth's magnetic fields have swapped cannot be explained by strong and weak magnetism. When molten rock reaches the surface of the Earth, any iron in it tends to quickly line up with the Earth's magnetic field. As the lava solidifies, it preserves the alignment to the iron and acts as a snapshot for the state of the Earth's magnetic field at that time. In some places, tectonic plates have been moving away from each other for millions of years, with molten rock continually rising to the surface and hardening and trapping the magnetic orientation of the iron within. The farther you get from the plate boundaries, the older the iron-filled rocks are, and the older the represented magnetic field is. Since the 1950s, scientists have been using sensitive magnetic measuring equipment to observe the flip-flopping magnetic direction over history with unwavering consistency. It's a matter of directionality, not strength.
Ugh, I forgot how painful this is. That's enough for today.
What do you mean for today? I can't wait around in hell. I've got to get back to Earth.
Dude, you listen to creationists and apologists for fun. Hell should be like a cool, refreshing breeze.
Could you at least ask people to subscribe to my channel, Paulogia?
I could, but no one ever listens to me.
I tell people to subscribe to Logicked.
No one listens to you either.